Hi. Today we're going to talk about heat versus temperature. So I want you to just watch this with an open mind and write down anything that occurs to you.
When you touch an object and it feels warm or cold, what is that really telling you about the object? Here I have a metal hard drive and a book, and I'm going to ask people to compare their temperatures. Which one do you think will feel warmer, the book or the hard drive?
The temperatures.
Yeah, tell me if one is hotter or colder, or if they're the same temperature. How do they feel?
This is slightly cooler than this one.
Yeah. Oh, that's warmer. Yeah. Way.
Yeah, agreed.
I'd say the hard drive is a lot colder than the book. I don't know, because the book's got more knowledge.
Why do you think that is?
Metal's normally a little bit chillier if you leave it in a colder temperature.
Well, what if I said that they're both at the same temperature? What would you say?
So you're lying.
But really?
I think you're lying, yeah.
Oh, jeez. Well, maybe the way I could prove it is I have an infrared thermometer. What do you think we're going to see?
I think science might be able to answer that. And I'm not a scientist.
Make a prediction for me.
I still think that's cool though.
Would you bet me money?
I do it because I don't have any cash, so yeah.
Let's measure the temperature of the book.
Okay.
What do you see?
19.0.
Okay. We measure the temperature of that.
19.0. Alright, well now I believe you.
I'm trying to actually figure it out, trying to figure out why they would be the same temperature. They don't feel the same temperature, though.
So why does that feel colder if they're basically the same temperature?
Good one. You got the answer?
Well, I'm coming to you guys for answers.
We're creatives, not intellectuals.
Well, create an answer for me.
I'm not a scientist. Come on, you tell me.
Well, I'll try to answer that question with another little experiment. Here is an aluminium block and
Ooh, nice and cool.
a plastic block. How do their temperatures compare?
Completely different. Completely different.
It's much colder.
Yeah.
Yeah?
Yeah, this actually feels colder.
Let's take this to the next level. I'm going to put an ice cube on both plates. What are we going to see?
Well, I'm guessing it would stay solid on this one and melt on this one.
So it's going to melt on the plastic but stay solid on the aluminium.
Yes, but maybe I'm wrong.
That one will melt more quickly than on the aluminium block.
Yes.
I think so. I think they're colder.
Yeah, because it's cold.
Let's
And I
actually...
think they're going to go the same.
All right, so we put an ice cube on each of those blocks.
Wow.
What are you seeing?
Well, it is melting a lot quicker on the aluminium.
My God, it's melting.
This is melting quicker than that one. Even though this is aluminium, that's plastic.
So which one felt colder?
That
This
one.
one.
How does that make any sense?
I have no idea,
Could aluminium be bad for the environment?
How would aluminium be bad for the environment?
Well, it's thawing out the ice a lot quicker, isn't it?
So you want the answer?
Yes, please. Please.
It's about thermal conductivity, right?
I'm not going to let him answer it. That's why I'm here, so I want to answer it. But clearly there's a lot of information here. The big problem is things feel cold and things feel warm even though they're at the same temperature. And it seems like they've got a backwards interaction with ice. So I'm not sure we're going to answer all of the questions. Maybe we'll come back at the end and finish things out. We're at 2:45. We'll see what he has to say. His name is Derek Muller. He's involved with a channel called Veritasium. It's all about science and misconceptions. So if you're not following him, it's probably a good idea to get involved with it. Why do objects feel hot? And I think that the most important, most salient way to talk about this is to delineate heat from temperature. Definitions are there. Basically, heat is energy that moves between objects because temperature is different. So heat depends on temperature. Temperature does not depend on heat. The units for temperature we've talked about before are degrees Celsius or Kelvin. We don't use Fahrenheit in this course. The units for heat are either joules or calories. You may have heard of calories before. You see it on the food label. It's based on that it's a measure of energy. We use joules typically in this course. To really put a point on everything with heat versus temperature, I want to share the second law of thermodynamics with you. It says it right there. Heat moves from hot to cold, higher temperature to lower temperature. Now, this is slightly misleading looking at the videos that we saw because the two objects were at the same temperature. But the second law of thermodynamics does not use the word feel. So there's a big difference between what happens, our perception of what happens versus what's happening based on thermodynamics. In terms of thermodynamics, as energy is transferred, temperature will change. When a hot object and a cold object touch, heat moves from the hot object to the cold object. The hot object cools down, and the cold object will warm up. So you can see, like, you'll see the temperatures come together, and then at some time, maybe the two temperatures would be the same, at which point, you know, the same amount of heat's going back and forth. The last thing I'll mention here is we do need to talk about delta T. That is a Greek letter delta, looks like a triangle. If you haven't seen it before in an algebra course, it means the change in something. So we're talking about the change in temperature. And the way we're going to represent that is either T2 minus T1, time 2, time 1, temperature at time 2, temperature at time 1, or final minus initial shown there. In terms of what you're seeing in this image here, the person who's on the beach feeling the sand be hot, what you can think of is when things feel hot, heat flows into you. If we were to use arrows to show how heat is flowing, the hot sand, which is higher than your body temperature on a sunny day, would be flowing into you, and that's how you perceive hot. The cooler water, which is at a different temperature, you would feel like your feeling of cold is actually the process of heat leaving you. The thing I did want to mention with this image, though, is they're both at the same beach with the same sun on the same beach. So why is it that you can see this different response? This is unlike what we saw in the video, but it's a related concept. So just to build on all of this and to start putting a little bit of math to it, it is worthwhile to talk about in this course measuring the quantity of heat, not just saying heat flows, but how much heat flows, because I think that would really put some light on the video you saw, and also you'll get maybe some concepts will start to be a little bit clearer. Like I said, there's your link to the reference tables. Looking at the top here, we have two images. This is just a glass of water. It looks to be about 6 to 8 ounces on a table, and this is a swimming pool. Clearly, there's a big difference in the amount of water that's present, but we can consider them both water. Yes, I know, chlorinated swimming pool. Let's just consider it water for now. I probably should add a picture of a lake. If you give both of these objects the same amount of heat, say 100 joules, which we don't really have a full concept of what that is yet, but you'll see soon. I would imagine that the swimming pool would have a smaller delta T, because the more water there is, the longer it takes to heat up. If you need a first-hand example of that, you should look at, say, I don't know, cooking up some water at home. If you ever boiled water, the less water, it boils a lot quicker when there's less water. It gets to that boiling point. But also, if you gave the same 100 joules, if you had like the cup of water versus a 5-ounce gold bar, that's roughly the same amount of mass, what you would see is for the gold, you'd see a larger change in temperature. And for the water, you'd see a smaller. So if we were going to rank the changes in temperature, this would have the smallest change in temperature, this would have the middle change in temperature, and this would have the largest change in temperature in reference to being given equal amounts of heat. And all three of these, folding these all together, we get to this idea of something called specific heat capacity. Because you can see different amounts of heat between samples of water of different mass, and you can see changes in delta T between samples of different substances, it's beneficial to kind of say this baseline thing. To say that specific heat is, we're going to measure the amount of heat needed to raise 1 gram of an object by 1 degree Celsius. So we're fixing both of those. So we're not comparing swimming pools and cups. For a frame of reference, just to give you some ideas about gold and water, water has a specific heat of 4.18 joules per gram degree Celsius, and gold has 0.129, so way less than 1 joule per gram degree Celsius. So again, now if we can use these numbers and relate back to this 100, if we gave 100 joules to 1 gram of water, you would see maybe a 25 degree change. And for the gold, if you gave 100 joules of energy into that gold, you'd see like 1,000 degree change. That's how those numbers manifest. Really, by putting the terms direct and inverse up here, I want to build this idea of saying as something increases, something decreases. So what we can see here between these two, if you have the amount of heat constant, as specific heat it seems to me that delta T is going to decrease. Or the other way around. As specific heat goes down, delta T goes up. It seems like also that's true of mass. As mass goes up, change in temperature goes down, based on everything I've said. Those two processes, those two phenomenon where you see one quantity increase and the other decrease, that's what is called an inverse relationship. We're going to see inverse relationships a lot in this course, so I wanted to build the idea in now. The idea is that when you have inverse relationships, typically those variables are multiplied. So hopefully this would help make things make a little bit more sense when talking about the formula to calculate heat. It is found on your reference tables on the back cover, Table T, again, link above my head. The general formula for a situation in which the temperature of an object changes is Q equals mc delta T, where Q is the variable for heat. Remember that the units are joules. M is the variable for mass. The unit is grams. C is specific heat capacity. You saw the units on the previous slide. That's joules over grams times degrees Celsius. It's a very weird unit, but usually that's how constants work. And then delta T is change in temperature, so the change would be in degrees Celsius. Again, your reference value for liquid water is 4.18 joules per gram degree Celsius. That's found on table B of your reference table. I did want to mention two things. Specific heat is unique to every substance and every phase of every substance. Solid water, ice, has a different specific heat than liquid water. Because the table B value is given to you on the reference tables, most questions you see on a Regents are going to line up directly with liquid water. If it isn't, you'll likely either have to calculate specific heat in the problem or you'll be given it in the problem. To give you a frame of reference for how this all will pan out in a problem, I have my calculator, I have my formula boxed out. I wanted to go through and solve a couple of these. So I'll go through quickly the process for the first problem, and feel free to pause this if you have the capability, if you'd like. For the second one, I won't go through the process as much, and I'll give you a chance to do it yourself. First step for me is to copy down the formula, and then I go back to the question, and I go find all the words that line up, or all the quantities that line up with those values. So it says how much heat, that's our Q. It says 50 grams, that's a mass. Water, that's going to be our hint towards our C, and increases by 30, so that's a change, it goes up. That's going to be our delta T. Now we just have to plug in all of our values. The amount of heat, it says how much, so that's not what we know. 50 grams of water, we're going to multiply that by 4.18 joules per gram degree Celsius, and the delta T was 30 degrees Celsius. Cancel out our units, and you'll see that's why the units for specific heat are so weird, because it makes all the units work out in the formula. And that gives me 6,270. Let's round that to 6,300 joules. So that actually gives me a little bit of information. 50 grams of water, that's, I don't know, about 2 or 3 ounces, and going up by 30 degrees Celsius. So that's a lot of heat compared to the 100 I was talking about before. Here's another problem, very similar, slight difference. If you want to try and solve it yourself, we can do that. I'll shut up and just write things out. We have two temperatures, so delta T is T2 minus T1. So in this case, it's going to be 38 minus 34. So in a problem where you're not given the change in temperature, but you're given the temperatures, you might have to do a little bit of math beforehand. And that comes out to 83.6 joules. We can call that 84, or even 80 if you really want to round it. I'm not too worried about rounding. That again gives you a frame of reference when you can see when the mass goes down from 50 to 5, the heat is a lot smaller. You get those relationships again. When the increase goes from 30 to 4, again it goes down. So we can even see that now there's some direct relationships between delta T and heat. As the change in temperature goes up, so does the amount of heat. Two more practice problems if you want to do these yourself. I actually want to I'll just work them out. If you want to pause or just work on your own, you can do that. Let me write these out. Just to talk about this answer for a second, notice that this word came in, this decreases in temperature. Turns out that the final temperature is lower than the initial, so delta T is 32 minus 40 is a negative 8. It is possible for heat to be less than 0, to have a negative number. We can see that this word here says released, where in the previous problem it said absorbed. And I think that's where we're going to tie those two together. When a substance absorbs heat, the Q, the heat, is positive. When a substance releases heat, the Q is negative. The Regents will sometimes let you get away with making this a positive 836 because the word released is used. I prefer not to do that, and I prefer to just stick to the positive and the negative. I actually find it less confusing. This one says absorb, so that tells us, and especially because the delta T is positive, that Q will be greater than 0. So try and do this one for yourself too, and let's meet after we solve it. So in this problem, we're not solving for the heat, we're solving for the mass. Works the same way, you just have a different variable. It says what mass of water, so I don't know if it's going to be helpful that once you see that, that will tell you the question word, right? Once the word that's next to the question word tells you what you're solving for. So we actually had a heat, 2,000 joules. You still solve it the same way. You get 95.7, 96, close to 100 grams of water to satisfy everything that's said there. In that case, like I said, the change was positive because it was absorbing heat. The temperature went up. To pivot to the last thing we're going to talk about today, remember when we talked about heating and cooling curves, when you went through that process, that there were two sections on your graph where the line was flat, where the slope was 0. You'll notice that there were 3 regions where there's a positive slope and then 2 regions where they're flat. The positive slope, everything we've talked about with the water getting heated up, that fell completely in this middle region of just the liquid. And you can see that as the heat is absorbed, the temperature goes up. You have this positive slope. For the parts where it says melting and boiling, though, over time, the change in temperature is 0. The water, the ice, the whatever is happening, the solid melting or the liquid boiling, the temperature isn't changing, even though heat is being dumped into it. This really harkens back to what you were seeing at the beginning in this video. The ice was melting, but as ice melts, the temperature stays at a constant 0, even though heat is continually transferred. So this breaks that rule we saw before, where the part where it said as the heat is transferred, temperature changes. There needs to be a little asterisk that says only when phase changes are not happening. So because of that, phase changes have a delta T of 0. You can't use Q equals MC delta T because heat is being absorbed, but if delta T is 0, then Q is 0, so this formula not going to work. There are 2 others found on table T of your reference table, link above my head, and they use 2 different terms, heat of fusion and heat of vaporization. The heat of fusion applies to substances going from the solid to the liquid phase. Yeah, fusion, but that's not quite, that is actually the textbook definition of what it means. It's not what we usually refer to it as. Just consider fusion to be melting. Vaporization is for boiling, and it's the substance, it's the quantity that for 1 gram turning into, from solid to liquid, the amount of heat. The numbers are found on table B of your reference table. You'll see that water, ice has a heat of fusion of 334 joules per gram. Water has a heat of vaporization of 2260. And that is also reflected in this graph by the fact that the boiling line is a lot wider than the melting line. Assuming the same sample of water, it takes a lot more energy to boil it than to melt it. In approaching problems where this happens, all you have to do is the same process. How much energy? We have a mass. It's another mass. You'll probably see 2 masses in these problems because you're talking about one substance, but you'll see it written as like 10 grams of steam and 10 grams of water. And then you're at the boiling point or the melting point. And that is the definition. You're going from 100 degrees Celsius to 100 degrees Celsius. The temperature can't change, or else we'd need those other formulas from before. Because it says steam and water, that's going to be our heat of vaporization because gas to liquid. So Q is going to be equal to mHV. Because it is condensation and not boiling, we could use the negative there. Remember, it says how much energy is released, so that kind of bends that rule for us. We're just going to plug in our values. 10 grams, and since it's that, the number on the table is 2260. So our number here is going to be, oh, that's too many 2s, a negative 22,600 joules, or I guess if you wanted to refer to it in, change that unit, it would be 22.6 kilojoules. Either one's correct because, units work like that. You can also see problems where they ask about what mass of water. You can do that one on your own. I'm going to write the answer out real quick. You get 5.99 grams, about 6 grams for the second one when solving for the mass. One big thing I want to point out here, you're seeing hopefully that the numbers for heat end up in general bigger. 22,000, 23,000. They end up bigger for the phase changes than they do for the change in temperature. That's not a hard rule, but it's definitely true of water. To sum things up, heat, we've got a definition for heat. It's based on a change in temperature. If two objects are not at the same temperature, heat will flow. That's a rule of the universe. And then heat will do that until hot isn't hot and cold isn't cold. Once they reach the same temperature, the heat will not have a directional flow. It'll go back and forth interchangeably. When the change in temperature occurs in the object, this is the mathematical formula we use to calculate. All the units are over there. You need the specific heat capacity found in table B. For the phase changes, you have two formulas. Depends on whether it's the solid to liquid or liquid to solid, or the liquid to gas, gas or liquid. Thanks for watching.